Before moving any further in the course, let me start with, or let me briefly discuss what is known as the hierarchy problem in physics. So before I discuss the Kaluza-Klein theory in somewhat of detail, I would like to talk about this problem, which is a question regarding gravity and the other forces. So, at the Planck scale, the effects of quantum gravity they become considerably important. So, remember, I mentioned in the previous lecture, the problem can be shaped in this way, that why is gravity so much weaker than the other forces, right, or other interactions. So again, the question is that why is gravity so weak when it is compared with all of the other interactions that are present in the current standard model of particle physics? Now, let me briefly show you the difference in the order of magnitude between these forces. So let's say if I draw this vertical line which shows you the energy, and corresponding to that I'll draw a vertical line which shows you the length at which these forces act. So now the Planck scale lies between where did that line go? Between the energies 10 raised to power 21, and this energy is in the units are giga electron volts, right? And the length would be in centimeters, right? So the Planck scale lies between 10 raised to power 21 and 10 raised to power 18. So the Planck scale lies somewhere over here, and we know that the length of this Planck scale is 10 raised to power 30 minus 33 centimeters, right? And then you have to go down by a very large amount, right, in terms of energy, and you have your weak scale over here. So let me write it down. You have Planck scale lies somewhere in this area, and your weak scale would reside in this area. So this is your weak scale, where the energy of your weak scale is 10 raised to power 3 giga electron volts. And you can see the order of the difference in the order of magnitude between these two scales is a lot. And the numerical value is, you can see that it's 16 orders of magnitude. The difference is of 16 orders, and the scale at which weak interactions happen is somewhere between 10 raised to power minus 18 centimeter and somewhere between 10 raised to power minus 15 centimeter, right? So this is just to give you a rough idea of the difference in the strength of your gravity and your weak interactions, or all the other interactions, right? Below this you get your proton mass and your electron mass, right? So below this you have your proton mass and you have your electron mass, right? So below this weak scale, right? So that's this. All right, now getting back to this thing. So you can see that gravity is much weaker than the other interactions of standard model, but there is a hope that the four-dimensional Planck scale might not be fundamental, right? And so the scale of quantum gravity is actually much smaller if you say that large extra dimensions exist. So what I'm going to do is I'm going to talk about some things about extra dimensions now, and you will get my point. And building up the knowledge of this extra dimensions using this problem, a hierarchy problem, we'll build up our concepts of extra dimensions, and then we'll go in the next lecture we'll go towards the Kaluza-Klein theory, where you will see how to deal with these kind of things in the Kaluza-Klein framework. So I'm going to start off by considering Newton's law. So let's just write it down over here. So let's start with Newton's law in let's say you have your normal 4 dimensions, and let's add some n to it. So in 4 plus n dimensions. Okay, so it's very simple to write this thing down. So I'll just write it down and you can figure it out yourself. So you write your Newton's law normally as f of r is equal to the Newton's gravitational constant, and this is Newton's gravitational constant, and multiplied by the two masses. One is the source and one is the test mass, and you have your r squared, right? So this is your regular Newton's law. Then you can, if I have to write it in 4 plus n dimensions, it's very simple. You can use dimensional analysis to even verify that this thing is correct. You have your Newton's constant in 4 plus n dimensions, right? And you have your test and source mass, and this is then divided by r, but you have n dimensions as well. You have 4 plus n dimensions, so you just add n to your r, this 2, right? So this is your Newton's law in 4 plus n dimensions, which can also be written as 1 over mpl, which is, this is the Planck length in 4 plus n, and you have n plus 2 over here. This is your, I have just rewritten this Newton's gravitational constant in terms of the Planck length times m1, m2 over rn plus 2. Okay, cool. Now, let's say you have your extra dimensions, and they are compact extra dimensions. I have given you the idea of compact extra dimensions in the previous lecture on compactification and identification. So let's say you have n compact extra dimensions, right, where this n is the same as this n, right, that we have been using, this n, right? So this one. So these two are the same. So what is n? N is basically your compact extra dimension. Now let's say that these extra dimensions have a size, and let's call it L, which is equal to 2 pi r. So these compact extra dimensions are S1, which means that they are a circle, and the length of these extra dimensions is just the circumference of this circle, right, where the radius of the circle is like this r. Okay, now the constrained lines from a source mass are to be compelled to go parallel in the extra or these additional dimensions when the distance within the regular 3 spatial dimensions is larger than this L. So you can then say that if I look at this case where my r is very small than the length of the extra dimension, so r is just your radius of the circle. So this capital, well, let me just write small r over here as well, and let's just write it like this. So okay, so no, these are not the same r. Let's not confuse you with that. So let's just put this r. This is r. But when you're this r between the two masses is much smaller than your size of the extra dimension, or in other words, the extra dimension is much larger than the distance between the two masses, you can write down your Newton's law in 4 plus n dimensions as 1 over mpl in 4 plus n raised to power n plus 2 times m1 m2 over rn plus 2 rn plus 2. Right, now if let's look at the other case as well, which is obviously if r is much greater than the extra dimensions. So let's say that the distance between the two masses is extremely large when it's compared to the extra size of the extra dimension, which you would normally we normally would see if extra dimensions exist. So then you'll have your Newton's law written as 1 over m n plus 2 Planck length 4 in 4 plus n, right? And you would have times m1 m2 over r squared. Now you'll only have r squared over here because you can see that the size of your extra dimensions much is much smaller when it's compared for this distance between the two masses. And then wait, I'm missing a factor over here, and that's obviously the size of the extra dimension, L raised to power n. So this is what you have when your distance between the two masses is very high or it's very large. Now next thing is that I'm simply going to compare this equation, which is this one, with your original Newton's law, the original four-dimensional Newton's law, which is this one. And if I compare these two equations on which I have marked them with the arrow, I arrive at the result that relates the Planck scale to the size of the dimension, or instead you can call it the volume of the compact extra dimension. And the result is it's very simple to get. You can just get it by visually comparing the two, and it's your Planck scale in 4 dimensions is approximately equal to your Planck scale in this 4 plus n dimensions multiplied by L raised to power n, where again n is the number of compact extra dimensions and L is the size of these extra dimensions. And you would have well, you know that L raised to power n is simply volume. So in a hyperspace, right? So you'd have m n plus 2, your Planck scale in 4 plus n dimensions, times v, which is the volume of the n compact extra dimension. Right, now next thing is to is to get the value for your length of the extra dimension in terms of how many dimensions you have, right? How many extra dimensions you have. So let's figure out how is the length of the extra dimensions related to the number of these compact extra dimensions. So that's also very simple. If you take the nth root of the ratio of the 4D Planck scale and the fundamental scale, so let me write it down. Your four dimensional Planck scale, which is MPL4, it is somewhat about 10 raised to power 19 giga electron volts, right? And the fundamental scale, which is which would be your, of course, 4 plus nd, right? So that would be MPL4 plus n, and that is approximately 1 tera electron volts. So just take the ratio of these two, and what you get is the size of the extra dimensions. You would have 10 raised to power 10 raised to power, well, let me write it down in terms of this quantity. So you would have L is equal to MPL of 4 over MPL 4 plus n plus 2, and we have to simply take the nth root of this thing to get because the reason is because this is L raised to power n, and to get rid of that you just take the nth root on both sides, and what you get is you get a value which is about 10 raised to power 32, and because of this nth root you would have over n as well, and this is in terms of tera electron volts raised to power minus 1, which if you write it in terms of centimeters, this comes out to be 10 raised to power 32 over n times 10 raised to power minus 17 centimeter. So this is the size of your compact extra dimensions in terms of the extra dimensions. So I'll just write it down over here. Size of compact extra dimensions in terms of number of these compact extra dimensions. Okay, cool. Now note that the standard model has been put thoroughly put through its paces for up to a few 100 giga electron volts to some tera electron volts, which basically implies that the standard model fields are not capable to propagate into the extra dimensions that have a size which is of r greater than equal to 1 tera electron volt raised to power minus 1. And so if there exists these large extra dimensions, then let me actually draw this and just say this one point to you before I end this lecture. You consider you have this thing which is called 3-brane, right? Let me just draw it. Okay, so this is a 3-brane, and on this all the fields of standard model are confined to this brane. So you would have your standard model processes, interactions, everything which is confined to this brane, right? So you live on this brain, and all the standard model is fixed onto this brain. But gravity is allowed to propagate whatever is outside this brain, and whatever is outside this brain is your extra dimensions, right? So if gravity is allowed to propagate outside these extra dimensions, then the particle of gravity, which is graviton, will be able to jump from this 3 brain and go into the extra dimension. So everything outside this extra dimension, so everything outside this 3 brain are your extra dimensions, right? So then the statement here is that if there exists large extra dimensions, then the standard model fields must be localized on this 3 brain, having it has a thickness of this brain has a thickness of about 1 tera electron volt raised to power minus 1. So we are going to talk about this 3 brain, and why do I say that the standard model fields must be localized on this 3 brain. We can mathematically write that down and see why is that the case. You would see that your equation of motion for some particles would tell you that that how these fields are confined to this this brain, while the other equations of motion for other particles will tell you that they are allowed to propagate, so they are free, they are not confined to anything. And then there is a case as well where you talk in terms of string theory, where you have open and closed strings, and your one of those is allowed to move or get away from this 3 brain, while the others are pinned on this brain and they cannot move away from the brain. So that's it for this lecture. Next time we're going to dive into the Kaluza-Klein theory for these extra dimensions, and we look at the framework of the theory, where I'll also talk about different various fields in that extra dimension. So for example, we'll mathematically describe the scalar field in 5 dimensions and gauge field in 5 dimensions, and finally we would also move on to discuss the gravity in 5 dimensions. So which is where we'll be I'll be discussing the decomposition of the Kaluza-Klein states, and will recover or will obtain what is called the propagators for the gravity Feynman rules, right? So that's it for this video.